Number 3, consider a sample of 10.0 grams of the gaseous hydrocarbon C3H4. To answer the following questions, sorry, that was horrible flow there. Sorry. To answer the following questions, my bad. A, how many moles are present in this sample? So we have 10 grams of this stuff. And we're going to be converting into moles of this stuff. In order to do that, we're going to use the molar mass of this stuff. Now, hopefully you can see just from the way I've set up the crosshairs, grams will cancel, moles will be the only unit that I have left. Well, the question asks for moles, so we're good to go there. What I need to calculate in order to put in here is the molar mass of C3H4. So over here on the side, I got 3 carbons, each at 12.01. I have 4 hydrogens. I'm just going to round a little bit. So it's going to be 36.03, 4.04, and that total is going to be 40.07. All right, now, again, this could be a formula mass or a molar mass. Right now, I want it to be a molar mass. So this is 40.07 grams per 1 mole. Now you can see that the crosshairs have told me that I need to divide this out. So I'll get my calculator. 10 divided by 40.07. I get 0.24956, yada, 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 yada. But I only want 3 significant figures, okay? Because this term right here, 3 significant figures, that means my answer needs to be reported with 3 significant figures. So I'm going to round to right here. This 5 tells me I want to round that up to 10, so I'm going to round that up to 5. So I am going to have a final answer. I guess I'll write it up here. 0.250 moles C3H4. B, how many molecules are present in the this sample of C3H4? So we have this many moles of the substance. Set up my crosshairs. Luckily, I have something that can convert from moles into molecules. That is Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd particles per 1 mole. So for every 1 molecule, I have 6.022 times 10 to the 23rd molecules. Now looking at the crosshairs that I've set up right here, I know that the moles will cancel, and I'm going to multiply these two scary, scary numbers. Again, I've said this before, but I want to reiterate since we haven't gone over this in a while. Treat the M value and the N value on these scientific notation values separately. It's just going to make things easier for you instead of typing the whole thing into your calculator. And you're like, oh, Mr. Johnson, why did I get this wrong? And I'll be looking at your setup. Your setup is correct. Did you just type it into your calculator wrong? You're like, oh, I don't know. And I don't know either because I don't know how to use your calculator. So I'm going to start by multiplying. Get that into view here. 0.250 times 6.022. Now, one thing I do want to point out, I noticed first off that that number is between 1 and 10, so just right off the bat, it doesn't look like I'm going to have to move the decimal at all, right? For the M value. I would have to move the value, would have to move the decimal if the value was not between 1 and 10, and then I'd have to change the exponent. But right now, that 1.5, that looks good to me for scientific notation. Doesn't look like I'm going to have to move the decimal. That means I'm going to get to have that times 10 to the 23 just stay the same. Okay, just stay exactly the same. Now, looking at the numbers that I'm using here, it looks like this 0.250 is limiting my significant figures to 3. So looking at the value, I get my calculator. I'm going to limit this to 3 significant figures. This 5 right here tells me that I want to round that up to a 1. So I will report 1.51 times 10 to the 23rd molecules. Lastly, let's look at C. How many carbon atoms are present in this sample? Not molecules, the C3H4, but specifically the carbon atom. Okay, so I know that for every, let's just start with moles here. So this is the stuff I have. This is the sample that I have. The 10 grams, the 1/4 of a mole. This is the sample I have. In this sample, how many carbon atoms do I have? This might seem very difficult to make a conversion factor if you're just trying to copy something that we've done up here. Like, let's keep this in concept land here. I need a statement of equality here, something that is equal going back and forth. I know that for every 1 molecule of this stuff, I have 3 carbon atoms, don't I? Yes, I do, and so do you. In that same way, for every 1 mole of this substance, I have 3 moles of carbon atoms. That's the same thing. It's a statement of equality. So I can actually use that as a conversion factor. For every 1 mole of that stuff, I have 3 moles of this stuff. And guess what? Moles of that stuff will cancel, and I'm left with a response that will be in moles of carbon. Now, that's not what the question is asking for. Okay, the question is asking for atoms of carbon, but I will have successfully gotten this to be talking about moles of carbon, just carbon. And then in the same way as I did on B, I can convert moles of something into particles of something. So use my nifty nifty calculator. So for every 0.25 moles of this substance, I have 0.75 moles of carbon. And so I'll take that 0.75 moles of carbon, and I will use Avogadro's number to convert into atoms. Moles will cancel, and so I'm left to do some multiplication. Come back, Mr. Calculator. 0.750 times 6.022. I come up with, again, a value that is in between 1 and 10. So, lucky me, I'm not going to have to move the decimal. That also means I don't have to change the exponent. Hooray. Okay, so, again, it looks like I'm limited to 3 significant figures by this 0.75. So I'm going to go 4.52. Looks like I got to round that up. 4.52 times 10 to the 23rd carbon atoms.